A stream of molten iron leaving the furnace carries more than metal. It drags slag, sand, oxides, and gas along with it, and any of those trapped in the casting becomes a crack, a leak, or a rejected part. A silicon carbide foam filter is the porous barrier that sits in the flow path and catches what the metal should leave behind, all while glowing at the same heat as the pore itself. The body is a reticulated web of silicon carbide struts. An open, three-dimensional network that is mostly empty space, so molten metal flows through it while the solid ceramic frame does the catching. That open structure gives a large internal surface for inclusions to stick to without choking the flow. When cold ceramic meets metal above 1,300 degrees, the shock can shatter a lesser filter on contact. Silicon carbide conducts heat about 10 times faster than alumina, so the strike spreads through the struts instead of concentrating at the surface, the reason it takes the thermal hit and keeps its shape. It holds its strength in service up to around 1,500 degrees and stays chemically stable against the aggressive molten iron and copper alloys washing through it, so the frame neither melts nor crumbles into the very casting it is there to clean. The fineness of a foam filter is measured in pores per inch. A coarse filter near 10 pores per inch passes metal fast and catches only the largest debris, while a fine one up towards 60 traps far smaller particles at the cost of flow. Choosing the number is a trade between how clean the metal must be and how fast it has to pour. Capture happens 3 ways at once. Debris too large for a pour is sieved out at the face. Fine oxides that do enter stick to the strut walls by physical adhesion as they wind through the tortuous path, and as those particles build up, they form a cake that filters finer still. The depth of the network is what lets it hold far more than a flat screen ever could. The network does a second job as it cleans. Turbulent, swirling metal that would fold air and oxide back into itself enters the foam and leaves it as smooth, parallel flow, so the metal fills the mold calmly instead of splashing, which cuts the gas porosity that turbulence alone would create. Foam filters come as squares and discs to suit the gating they drop into. Squares commonly span from about 40 by 40 millimeters up to 200 by 200. Discs from roughly 40 to 200 millimeters across, with a thickness usually around 20 millimeters to give the flow enough depth of network to work through. Selecting a size is a balance of pore weight and flow. The face area is matched to the mass of metal a single filter can clean. Rated per unit of area for gray or ductile iron. While shape, thickness, pore density, and an edge chamfer or seal are set to the runner it sits in, so the metal passes through the foam rather than slipping around it. Seated in the runner of an iron casting, the filter meets a strike of gray or ductile iron poured between roughly 1,300 and 1,450 degrees. Graphite clusters, sand washed from the mold, and slag from the melt hit the foam and stay there, while clean metal threads through the network into the cavity. The thermal shock resistance is what lets the cold filter take that first strike without cracking, and the depth of the pore structure is what lets it keep capturing as the pour continues. So the inclusions that would have become hard spots or leak pads are left in the filter, not in the part. Broken out and sectioned, the casting comes through with fewer inclusions, less gas porosity, and a smoother machined surface than the same pour run without a filter. The laminar flow the foam imposed shows up as sound metal where turbulence would have left oxide folds. Cleanly, a single porous block sitting in the runner decides how much of the melt becomes a good part and how much becomes scrap, the small piece that guards the whole casting.